let's look at something in field theory. So a field of finite order p to the n, also find a finite field or Galois field, is a central object in abstract algebra. So we have some basic facts. P represents prime numbers, n is positive integer, and p to the n elements is a field with p to the n elements is denoted f sub p to the n or gf of p to the n. And such fields exist for every prime p and integer from 1 on, and are unique up to isomorphism. So yeah, that's why with isomorphism also isomorphic objects, they must have the same cardinality if they're isomorphic, so amount of elements, number of elements. So that's why we also, I think, characterize them by the number of elements p to the n here, depending on prime and integer power. So case 1, n is 1, that's fp. We have the n is 1, so f sub p to the 1, so f sub p, the base first exponent. So with arithmetic modulo p, so example is f sub 5, 0, 1, 2, 3, 4. Okay. So if n is bigger than 1, they're polynomials of degree strictly smaller than n, with coefficients in f sub p. So these elements will look like polynomials from a0, then a1 times x to the first until a n minus 1 to the x to the 1 lower than n. And there's a key detail Chad tells us. So these polynomials are taken modulo an irreducible polynomial of degree n. Modulo an irreducible polynomial of degree n. So 1 degree higher than the max term in this polynomial. The highest is x to the n minus 1 we see here. This modulo an irreducible polynomial degree n, which is 1 higher than n minus 1. Oh, and then we have introduction to construction idea. So if we, this is like an interesting construction. So f sub p to the n, we will start with polynomial ring f sub p of x. So, and then we choose irreducible polynomial f of x of degree n and form the quotient. So it's like with quotient groups, the same notation with a slash here. And whatever this is, then we basically construct this thing. So let's ask for an example, or we are given an example. So f sub 2 to the 2. 2 is prime and 2 is as exponent is integer. Everything satisfied. So we must use the field 1 lower than the 2 itself, so 0 and 1. And we choose irreducible polynomial x squared plus x plus 1. Elements are 0, 1, x, x plus 1. Arithmetic is done modulo f of x. So x squared is x plus 1. Interesting. So there is additive structure. So it forms a vector space of dimension n over f sub p, and there is exactly p to the n elements. And multiplicative structure, all non-zero elements form a cyclic group. And cyclic group, by the way, is basically you take one element, you keep multiplying it, and you generate all the remaining elements in that group. So that means cyclic. Yeah, that's what they say. There exists a generator G such that G to the 0, G to the 1, so on. And key take element of the finite field are either integers modulo p or polynomials of degree strictly smaller than n with coefficients in f sub p, taken modulo an irreducible polynomial. I mean, we were just introduced to some examples, so I guess at least we got some initial intro.